Hi, one of my friends, Steve Mould, which is also a great science YouTuber, told me about an issue with LED lights. Most of my friends are called Steve. Helps me remember their name. Like and subscribe if you're also a Steve. Basically, Steve describes in his video, which is a companion to my video, that when you turn off the light switch, some of the LED lights never quite turn off.
And it stays on. Can you see it's still glowing?
I have heard of this problem in different forms. Like some people said, when they touch the body of their desk lamp, the LED light starts glowing. But the problem is that I have the LED lights all over the place at home and I've never seen this problem. So I had to go buy these light bulbs that have such problem. Let's get them to glow. These lights won't fit my light socket, so I'll connect them using my alligator clip. You shouldn't forget to turn the light off or open the breaker before working on your electricity. Okay, so I can turn it on, but when I turn it off, it doesn't glow at all. Whatever. It's not made for my socket anyway. Ooh, hey, look at this. Okay, apparently that's connected to the live wire, but I'm not connected anywhere, and probably that's why it didn't shock me. Yeah, no. Well, look at this. It's glowing. I love discovering by accident. See, I am isolated from the ground, but there is a super small capacitance between my body surface to earth that when I touch the other terminal of the LED, a super small current runs through my body and makes the LED glow. So in those cases where the LED still glows, there must be some capacitance in the house wiring. And Steve helps me uncover that mystery in his video, which you should watch following the card here or the link in the description. After I'm done here. And you should definitely subscribe to him. His science voice is so soothing, I watch him for therapeutic purposes.
If you like him, think about subscribing. Do you know what? Just subscribe. It's a good channel.
Okay. But now we know these lamps are super sensitive and are different from the other type. These lights are so sensitive that if I connect one terminal to ground through my faucet and hold the other terminal and rub my foot on the carpet, it glows from the static I'm creating. Let's measure the current. You never touch the live wires. I'm what you call a professional dumbass. Now here, the LED light is only connected to the live wire and the other terminal goes through the ammeter where I touch. And my feet are off the ground, and if I touch it, you see a tad bit of glow there, and the current is around 2 microamps. Now if I put my feet on the tiled ground, you see it goes much brighter. I still don't feel anything. The ground provides a much higher capacitance, but it is still not conductive, and the current is around 40 microamps. Now what if I touch the ground wire with my pinky and close the circuit? This might give me a shock. Okay, it's not shocking me. And the current is around 130, 40 microamps. Very small. Now let's measure the voltage across the lamp in these different modes. Right now my foot is off the ground and the voltage is around 60 volts. And with my feet on the ground, it is around 70 volts, and through my finger, it is like 73, 74 volts. So although the current between these different modes changes significantly, the voltage doesn't change much. This is the behavior of the diodes. There is a bunch of LEDs or light emitting diodes in series in this light bulb. When we increase the voltage across the series, initially the current is close to zero until we hit a threshold, at which point the current increases significantly but the voltage doesn't change much. Somewhere around here the LEDs are fully on, and above that it probably burns. Now let's try the same thing with a regular light bulb, although I can't see the LEDs well. What is it? Plastic? What is this? Titanium? Whew, here we are. Fewer but higher power LEDs on some sort of heatsink. Okay, with the live wire connected, measuring the current, with my feet on the ground there is still no glow, although the current is around the same 40 microamps. Now if I touch the ground, what? Ow! That's it! No more using my body as a capacitor. For sakes, I have capacitors. I'm not gonna use my finger no matter how convenient it is. Although, using a capacitor doesn't really show the change of body to environment capacitance. Anyway, I don't think I need it anymore. So the circuits between these two lights are different. One acts like a bunch of diodes in series while the other one doesn't. It can pull some good amount of current without any glow. It behaves more like an incandescent light. If I close the circuit through my fingers, almost the entire AC voltage falls across my body because the resistance of the light is much smaller than my body. And that will shock me to the moon and there won't be any glow. I need to cut this light open to see what's going on. Fortunately, it's only potted with a clear, flexible material I can easily dig into. And now I do some measurements to figure out the circuit. There we go, this is our circuit. The AC first passes through a capacitor, then goes through the full bridge rectifier. Get the merge! After it's rectified, the rectified positive waves go through two resistors, each powering a string of 32 LEDs in series. The 1 mega ohm resistor discharges the capacitor in case there is any DC buildup across it. But the purpose of the capacitor itself is not to block DC, but it reduces the AC voltage level. See, when we have two impedances of Z1 and Z2 in series, like a capacitor and a resistive load, then the input voltage divides between the two impedances, with the output being equal to input times Z2 over Z1 plus Z2, which means... What? The math is too hard for you? Why don't you head to brilliance.org, the sponsor of this video? They have tons of professionally made math and science courses with interactive problem solving and quizzes that help you learn very efficiently. Sign up for free at brilliant.org/electroboom and you get free access to a lot of courses already. But using my link, you can get 20% off of annual premium subscription that gives you full website access for less than $10 a month. I'll make you learn things one way or another. So the capacitor limits the voltage across the LEDs because they need around 90 volts to fully turn on, while the peak of the 120 volt AC is 170 volts. And the purpose of the full bridge rectifier is to make sure the LEDs turn on both cycles, not just the positive cycle. So voltage drops across a capacitor. But the good thing about a capacitor is that it only uses reactive power and doesn't waste real power and doesn't heat up. A simple and effective AC voltage divider. But a bad thing about this circuit is that at low voltages there is no current through the circuit, and no current means no voltage across the capacitors, so the output voltage can rise with the input voltage to a level that the LEDs will conduct and glow. So even a straight capacitor in the wires can make the LEDs glow. All it takes for the manufacturer to fix it is to add a very large resistor like 470 kilo ohms to the output of this rectifier to draw current and load this very weak voltage and reduce it to a lower level. So now I added a 470 kilo ohm resistor at the output of the rectifier and the light still turns on normally, but now when I touch the other terminal, it doesn't glow anymore. Only when I close the circuit with my finger, it shocks me a little bit now, it glows a little bit, which means that I have to reduce the resistor to suck more current. Very easily fixable. Also, if you place a proper LED light or incandescent light bulb parallel, ouch! Stupid loose wires. If you put a proper light bulb parallel to this light bulb, it sucks current and shorts the voltage across it and it turns off. The stray current that causes these LED lights to glow still exists in the case of other LED or incandescent light bulbs that waste a few milliwatts of power, insignificant. Just that these lights fully turn off because they need a higher current to operate. Now let's break this one open and see what's its circuit. Here I pulled everything apart. There is fewer LEDs in series, which means it requires less voltage to turn on, and I can still make them glow outside their circuit. I'm happy to announce the presence of the full bridge rectifier here that creates 170 volt DC. And this is a switching DC to DC converter chip that, along with an inductor, provides a proper DC across the LEDs. I couldn't find out the data sheet of the controller, but this is what the circuit looks like. Basically, the controller controls this switch using pulse width modulation, and every time the switch is on, the current rises through the diode and the inductor like this. And when the switch is off, the current loops through the Schottky diode and drops like this, and the ripple continues. The capacitor is to make sure the voltage across the LEDs is as fixed as possible, and the controller senses the current through the LEDs to regulate it accurately. The circuit between different lamps can be different, but such circuit requires a few milliamps of current to start operating, so a few microamps of leakage current through the wires won't turn it on, and that's why it doesn't glow. So there you have it. If this video excites you to solidify your knowledge in math and science, then head to brilliant.org. It provides great details to teach you a subject, and you learn by solving fun problems and taking quizzes. Very well prepared. I used to be super good at geometry like 25 years ago and wanted to refresh my memory, so I took their Geometry Fundamentals course and got hooked on a series of cool problems. And I got 100% correct, baby, at least for level 1. Plus, it was actually fun, like playing a game. So if you really want to advance in math and science, learning what you like professionally at your own convenience, go to brilliant.org/electroboom and sign up for free and get 20% off for the first 200 viewers. And thank you for watching.